We're dealing with a curve for which at each point of the curve, the normal line at that point passes through the fixed point 1, 0. Let's try to illustrate this partially by drawing a figure. Here is our coordinate system. Here we have the point P with coordinates 1, 0. And here we have a normal line which must pass through 1, 0. And at some point in the curve, it meets its tangent line. So this point over here, T, with coordinates x0 and y0, is the point where the normal line was calculated, for which the normal line was calculated, and other such points can be constructed in a similar manner, but the condition that for all such points the normal line must pass through fixed point 1, 0 must be met. It's not an easy construction, at least not until we know what kind of curve y really represents. Let's start by solving the part A, showing that y satisfies this differential equation. We'll start from the equation of a normal at point x0, y0, which belongs to a graph. So we have y minus y0 is equal to minus 1 over y derivative at x0 multiplied by x minus x0. This is the slope of a normal. So this is the equation of a normal to y is equal to f of x at the point x0, y0, which belongs to the graph. We know that the point P10 belongs to the normal. Therefore, it satisfies this equation. To be more precise, x is equal to 1 and y is equal to 0 satisfies the equation. Let's plug this in. So we have 0 minus y0 is equal to minus 1 over y prime at x0 times 1 minus x0. Since we are looking for the differential equation such that y prime is on the left hand side and it's positive, we will multiply this equation by minus y prime at x0 over y0. We need to be mindful that y0 cannot be 0 for this multiplication to work. So here we obtain y prime at x0 on the left hand side, and we obtain 1 over y0 times 1 minus x0 on the right hand side. Now, since x0, y0 is any point on the graph y is equal to f of x, we can generalize and replace x0, y0 with xy. Therefore, we have y prime is equal to 1 minus x over y. And this is the differential equation that was given to us. Now that we've solved A, we can solve B using separation of variables. For that, we will write down dy over dx instead of y prime. Everything that deals with y will be on the left hand side, and everything that deals with x will be on the right hand side. So this is 1 minus x times dx, and this over here is y times dy. We can integrate both sides of the equation. We obtain y squared over 2, and over here we obtain x minus x squared over 2 plus c. This constant c is a real number, but it depends on the initial conditions given for the differential equation. In this case, we are not given initial conditions, so we actually have a family of curves that satisfy this differential equation. We can also write this equation down in a more palatable way, so that it shows exactly what kind of curve we're dealing with. This is necessary for the part C, so let's do this. We can transform and place everything except for C on the left hand side. So we have y squared over 2 plus x squared over 2 minus x is equal to c. Then we can multiply this by 2. X squared plus y squared minus 2x is equal to 2 times c. I will call it k. But here it is quite obvious that we are dealing with an equation of a circle. This x squared and this minus 2x we will use and write it down as x minus 1 squared. But we borrowed 1 over here, so we have to be careful. We have plus y squared, and we would have minus 1 over here is equal to k. But in general, this is an equation of a circle, so we can write it down as x minus 1 squared plus y squared is equal to r squared, where r is equal to k minus 1. Sorry, r squared is equal to k minus 1. This is obviously a circle with a center at 1, 0. So the center of a circle is at the point P. And radius r. Of course, r is greater than 0. So let's just draw the corresponding circle for our figure. Over here, its center is here at P, and it passes through the point T. We will get some help over here. So let's draw. And we got some help. And here is a sketch of one of those circles, but the answer are concentric circles. Actually, it's not just a single circle, but concentric circles with a center at P1, 0 and radius R, which is any real number greater than 0.